In this video, we will introduce what L'Hopital's rule is. So sometimes to abbreviate the rule, I'll write LH. So LH will stand for L'Hopital's. Okay, so I want to begin with a question. How do we evaluate indeterminate limits that are either not simplified easily, not easily simplified, or two, what if they're impossible to simplify? So impossible to simplify. So let's give an example. So an example of an indeterminate form that's impossible to simplify is something like the limit as x approaches 0 of ln of, I'll do 1 minus x plus x all over x squared. So with this limit, when we plug in our value, when we plug in 0 into this, we will end up getting 0 on the bottom, and on the top we'll get ln of 1 plus 0, but ln of 1 is 0. So in the numerator we also get 0. And 0 over 0 is an indeterminate form. It's one of our indeterminate forms. So just as a review, remember indeterminate forms are things like, for example, 0 over 0, or plus or minus infinity over plus or minus infinity. Those are the two most common ones that we've seen. A couple of others that we've seen are 0 times infinity. This one we've seen less frequently. We've also seen infinity minus infinity. And those are the ones that we really see the most in this class. There are others, and I'll mention them at the end of this section in a later video. But for right now, let me just put comma, etc. So there's more of these, but those are the four most common ones. Those are the four ones that we'll see in our class. Alrighty, so when we do have an indeterminate form that we run into that is either not easily simplified or we just can't simplify it, like this example here, one strategy is to try using this rule, L'Hopital's rule. Alright, so let's state what the rule is and then look at some examples. So this is a theorem. It's something that can be proven. So here is L'Hopital's rule. It says that if f and g are differentiable, and when we look at the limit as x approaches a of f of x over g of x, if that limit has the form 0 over 0 or plus or minus infinity over plus or minus infinity, then the limit as x approaches a, so our limit of f of x over g of x, will be equal to the limit as x approaches a of the fraction where we take the derivative of the numerator and the denominator. So f prime of x, take the derivative of the numerator and take the derivative of the denominator separately. So important thing about this is not quotient rule. This is not quotient rule. That is super, super important. We're just taking the derivative of the top and of the bottom individually here. And that's not what we do with quotient rule. Okay, so it turns out this will be a formula for this limit, provided that this resulting limit, the limit as x approaches a, of f prime of x over g prime of x exists. So there are many examples in which we'll run into a limit of these forms, and using L'Hopital's rule to try to take the derivative of the top and of the bottom will be simpler than using our previous methods for evaluating these indeterminate forms, which was to simplify. So let's look at an example. So let's say I want to evaluate the limit as x approaches 2 of this function here. So remember, our first step with the limit is we try to plug in. And if we plug into this, we'll get 3 times 2 squared. Well, 2 squared is 4. 4 times 3 is 12. So we'll get 12 minus, and then 10 minus 2. On the denominator, we'll get 4 minus 4. All right, so the numerator is 0 and the denominator is 0. So this is an indeterminate form. Indeterminate form. So first, let's do this using our previous knowledge. So I'll call this method 1. Method 1 is going to be, let's simplify. This is using our Chapter 2 knowledge of limits. All right, so if we simplify, so we get the limit as x approaches 2. We'd want to try to factor the top and the bottom. Okay, so the top does factor, and so does the bottom. So they both do factor. I think the bottom maybe is a little bit easier. That's just a difference of squares. Well, x minus 2 and x plus 2. And for the top, I'd encourage you to pause the video and try to factor the top on your own first for about 20 seconds. But that's such a short period of time that I'll just keep talking about it right now and trust that you're going to pause it to try it. All right, so the top factors is 3x plus 1 times x minus 2. And now looking at this is nice because the x minus 2's will cancel. And after they do, now we will be good to plug in. So plugging in 2, we get 3 times 2 plus 1 on the top. On the bottom, we'll get 2 plus 2. And now simplifying, this is 7 over 4. And that's our answer. So we get 7 over 4. So not too bad. We just had to factor the top and factor the bottom. But that wasn't too bad because these are just quadratics. Okay, so now let's do this another way. So method 2. Let's do this using L'Hopital's rule. L'Hopital's rule. Okay. So using L'Hopital's rule, so first off, I can apply L'Hopital's rule because I had a limit of the form 0 over 0. And that's one of the forms I can use L'Hopital's on. The other being plus or minus infinity divided by plus or minus infinity. Okay, so L'Hopital's rule says we'll get the limit as x approaches 2. And actually, before I get into what this will be, let me make sure that I indicate to my reader that I'm using L'Hopital's. So the way I like to do that is I like to write the letters LH above the equal sign at the step where I'm using L'Hopital's rule. This is how I indicate to whoever's reading this, or maybe whoever's grading my work, that, oh, I'm indicating to you that we used L'Hopital's at this step. So that is really important when you are doing your write-ups, when you're doing your homeworks, when you're doing your quizzes or exams, that you indicate the step at which you do L'Hopital's rule. So it's easier for whoever is reading or grading your work to know that's what you did at that step. All right, so with L'Hopital's rule now, we end up taking the derivative of the top, which is 6x minus 5. And then on the bottom, I write the derivative of the bottom, which is 2x. Okay, so again, this is not quotient rule. I'm taking the derivative of the top and of the bottom individually here. Okay, so we've done those derivatives. And now let's try plugging in. If I plug in, I get 6 times 2 minus 5 on the top, 2 times 2 on the bottom. And overall, this is 7 over 4. And that's nice because that's the same answer that we had by simplifying this. So same answer, which is good. Same answer. But the main advantage to doing it with L'Hopital's rule, as opposed to doing it by simplification, is that in general, doing derivatives is quicker than trying to come up with a factorization. So there are always exceptions to that. So some expressions are going to be easier to factor than others. But both of these derivatives are really quick for us to do. And then from there, it wasn't too bad to just plug in. Let's look at some more examples. All right, so here is example 2. So we have this limit as x approaches 0 of ln of 1 minus x plus x divided by x squared. Okay, so at this point, pause the video for about 3 minutes to try this question on your own first. So 4, 3, 2, 1, pause the video. Pause the video for 3 minutes to really try this question on your own. Alright, so hopefully you did that and pause the video to try this first. Let's talk about it together. So this was one of the examples that I gave in the beginning of a limit that's an indeterminate form that we just can't simplify. I can't, because of the ln on the top, there's nothing I can really do to factor the numerator more. That would lead to a cancellation on the denominator. So let's first just check what we get when we plug in 0. We've already seen this in indeterminate form, but let's just write it again. if I plug 0 into this, we get ln of 1 plus 0 on the top, and 0 squared on the bottom. So ln of 1 is 0, so the numerator is going to be 0. And the denominator is definitely 0, so this is an indeterminate form. So we can't simplify this. Let's do this using L'Hopital's. So I write my equal sign. Remember, I write my LH to indicate I'm using L'Hopital's at this step that I'm about to write. So it's the limit as x approaches 0. So now I have to take the derivative of the top and of the bottom individually. So to take the derivative of ln of 1 minus x, I need the chain rule. Derivative of ln of stuff is 1 over the stuff. And then we multiply it by the derivative of the inside, the derivative of 1 minus x. So we've done more of these chain rule examples right now. So more and more, instead of writing d dx of the inside and then evaluating it on the next line, I'm just going to go ahead and start to write what this is. So the derivative of 1 minus x, the derivative of 1 minus x is just negative 1. So more and more, I'm just going to start to do that on the same line. Okay, so that's the derivative of ln of 1 minus x using the chain rule. The derivative of plus x is plus 1. And then the derivative of the x squared on the denominator is 2x. So again, we're not doing quotient rule here. Rather, L'Hopital's rule says take the derivatives of the top and of the bottom individually. Okay, so we've done L'Hopital's rule. Now let's try plugging in and see what that gives us. So if I plug in 0, we'll get negative 1 over 1 minus 0 is 1, and then plus 1. And then on the bottom we have 2 times 0, which is 0. 2 times 0, which is 0. So overall, we have 0 on the top, 0 on the bottom, which is indeterminate again. So we are going to try, maybe let's try L'Hopital's rule again. We got 0 over 0 again. So maybe we try it one more time. Okay, so we're doing L'Hopital's again. So let me write LH over this equal sign. And actually, you know what? Before I do L'Hopital's rule, let me think a little bit about how I'm going to take this derivative. Because seeing this negative 1 multiplying 1 over 1 minus x, I think maybe let's try to simplify that first and then take the derivative. So first, I'll write the limit as x approaches 0. And this negative, let me just move it to the front here. And then I can actually avoid having to do quotient rule. If you take the 1 minus x, we bring it to the numerator. So 1 minus x, bring it to the numerator. But now the power is going to be a negative 1. So I haven't taken the derivative yet. I'm just simplifying it. Okay, and then I still have this plus 1 after that. And then all over 2x. All right, so far just simplifying. Now, let's take L'Hopital's rule and take the derivative of the top and the bottom. Okay, so rewriting that term is going to let me avoid quotient rule. All right, so we got the limit as x approaches 0. Now the derivative for the top, I'm going to need chain rule for this 1 minus x to the negative 1 power. The power comes down, and I'll get positive 1, and then times 1 minus x to the negative 2, because I subtract 1 from the power. And then we multiply by the derivative of the inside, which is negative 1. And then the derivative of 1 is 0. And then all over, so the derivative of the bottom is going to be 2. All right, so now let's simplify this, and then we'll plug in. All right, so we got the limit as x approaches 0 of, I can bring this 1 minus x to the negative 2 and rewrite that as a fraction. And then this negative 1 we'll have in front of that fraction. So negative 1 over 1 minus x squared all over 2, that 2 on the denominator. Now let's plug in. If I plug in now, we'll get negative 1 over 1 squared all over 2, and that's just negative 1/2. And that's my limit right there. So that's one of the benefits of having this rule available to us. It lets us be able to evaluate limits that we couldn't evaluate previously. Because before, I wouldn't have been able to simplify this. L'Hopital's rule gives me a way around that by using derivatives. Okay, let's do one more example in this video. So now let's do the limit as x approaches infinity of ln of x divided by e to the x. So first step is we try to plug in. And plug it in, we'll get ln of infinity on the top, ln of infinity. On the bottom, we'll get e to the infinity. And for both of these, we need to remember what the graph of e to the x and ln of x look like. But we've seen those before. So ln of infinity is infinity. Same thing with e to the infinity. It's also infinity. If you're unsure about how I got those, definitely use our resources for help to ask. I want to make sure that you know why ln of infinity is infinity and why e to the infinity is infinity. Okay, but this is one of our forms that we can use L'Hopital's on, having infinity over infinity. So let's use L'Hopital's, LH, for L'Hopital's. So let's write my equal sign. I'll write LH over it to indicate I'm using L'Hopital's rule. We'll get the limit as x goes to infinity. And then we take the derivative of the top, which is 1 over x, and the derivative of the bottom, which is e to the x, individually. So we can simplify this. This is equal to the limit as x approaches infinity. And then this whole fraction will become 1 over x e to the x. Alright, so we just simplified that fraction. Now let's try plugging in. If I plug in, we'll get 1 over infinity times e to the infinity, which is 1 over the infinity times e to the infinity, we know is infinity. So we have 1 over infinity squared, which is 0. This is going to be 0. And that's our answer. So now that we've done these examples with L'Hopital's rule, you might be wondering, why haven't we always done limits like this? L'Hopital's rule looks easier than what we've been doing before with simplification. And there's a few reasons for that. The first reason is L'Hopital's rule involves a derivative. But we needed limits to define what a derivative even was in the first place. So we needed limits to lay the groundwork for derivatives, and derivatives are needed to explain what L'Hopital's rule is. So it doesn't make sense actually to talk about L'Hopital's as our first method for evaluating a limit for that reason. The second reason is when we evaluated indeterminate form limits, by simplifying, I think it makes more conceptual sense why simplifying works as a method. Like why simplifying and canceling something on the top and the bottom, and then plugging in gives us the correct value. Whereas with L'Hopital's rule, I think it's a little bit less, it makes a little bit less conceptual sense. Why should taking the derivative of the top and the bottom give me the same limit? Why doesn't it change the value? It seems a little bit more magical that L'Hopital's rule ends up working. And then maybe the third reason is, when we evaluated our indeterminate form limits, when we first talked about them in Chapter 2, using simplification, that was valuable to us in this class because we're going to be simplifying expressions throughout the class, not just in limits. We're going to be doing it in derivatives in Chapter 4, like we've seen. We're going to be doing it in Chapter 5 and on. All right, so in terms of our goals for this section, we have introduced what L'Hopital's rule is, and we've talked about that it applies for limits of the form 0 over 0 or plus or minus infinity over plus or minus infinity. In the next video, we will discuss a common mistake, a common error that I see when folks try to use L'Hopital's rule.